Okay, magnetism and matter. As we said earlier, magnetism is due to the movement of the electrons in atoms, so different materials, depending on their electron structure, will have different types of magnetic properties. Again, we can model it this way. We can imagine that an electron going around the center of a nucleus, if it actually did go around the way it's shown right here, would generate a magnetic field with a magnetic moment, because the electron is negative, would be in the opposite direction of the angular momentum. When we do chemistry and we look at different quantum numbers, of course, we talk about angular momentum related to the different orbitals that you have, orbital angular momentum, that sort of thing. And that is the classical analogy right here to physically what's happening in the quantum world. But in the classical model, we have all these particles, the electron, actually spinning like a top, and this creates the magnetic spin numbers that we have. And again, this gives the electron a magnetic moment, which of course makes it generate a magnetic field. So looking at the magnetic effects due to the electrons, the field due to the spinning is generally stronger than the field that we get from the orbital angular momentum. So basically, with electrons, when they pair up, one pair spin up, one pair spin down, that typically knocks out any net magnetic field. It's when we have unpaired electrons, especially in the d and the f orbitals, that we get magnetic materials. So again, in some materials the spins don't naturally cancel out. These types of materials tend to have large magnetic fields, and that's where we find our ferromagnetic materials. These materials which will retain a magnetic field even when we remove an external magnetic field. Large group of these atoms, when they come together, form what are called domains, and when an external field is applied, those domains can maintain that magnetic field to remain magnetized. We talked a little bit about domains before. When something is ferromagnetic but it's unmagnetized, all the domains are pointing in different directions. When we magnetize it, we grow those domains that tend to be more oriented with the external magnetic field. Magnetization. Okay, magnetization. The presence or absence of any significant magnetic momentum will basically govern how the atoms, if we picture them as little magnets, little magnetic dipoles, will behave. Here we have an atom not in a magnetic field. Its dipole moment can be pointing in any direction, but since we apply this magnetic field, there'll be a preference. There'll suddenly be a torque trying to cause this atom to align with it. Now, magnetization is a vector that basically is related to what is the total effect of the orientation of these atoms. Okay? And usually this magnetization becomes larger and larger as we apply an external magnetic field. So again, if we have completely randomized atoms, the magnetization is zero. But as they line up with a magnetic field more and more, the contribution to the total magnetic field, the magnetization becomes larger and larger. So again, without a magnetic field, domains tend not to be aligned with the magnetic field. They tend to align with this external magnetic field and enhance the local magnetic field there. So if we look at the total magnetic field, okay, we can look at it in terms of an external magnetic field, which is going to align these domains, plus here's a constant permeability free space, mu 0, times the amount of magnetization. Okay? So external, internal, the total magnetic field that we get is the sum of both. And that's why we'll oftentimes use ferromagnetic materials in the cores of electromagnets. Okay? The external magnetic field is created by the electromagnet. The internal magnetization of the ferromagnetic atoms will enhance that. Now sometimes it's convenient to replace B0 with H. This basically puts H on par with the same units that we have with M. Remember, this is measured in Tesla, this is measured in Tesla. These units would not be the same because you have this constant that has its own units. So sometimes you'll see, just to complicate things, instead of B, mu 0 and M, you'll also see this H. And again, H is just to normalize the units so everything has the same units. So B0 is basically mu 0 times H. Mu 0 times M gives you the contribution of the magnetic dipoles. So again, rewriting this, the entire magnetic field due to an external magnetic field, okay, and due to the field effects of the material itself, can be written like this. Now here's something called magnetic susceptibility. Magnetic susceptibility relates how much magnetization we get given the presence of some external magnetic field. If something is very susceptible, okay, it tends to align very easily with an external magnetic field. High magnetic susceptibility is found in things that are ferromagnetic. A low magnetic susceptibility means that it's very difficult to align any magnetic domains that are there with the presence of a magnetic field. So again, the expression for the total magnetic field can be written now by mu m. Mu m is a contribution from our external magnetic field once again, and also the contribution from the susceptibility of this. So sometimes you'll see this magnetic permeability written instead of talking about the magnetic susceptibility. Magnetic permeability again has the same units as mu 0, and again if it's greater than mu 0, then we tend to have a magnetic material. Okay, classes of magnetic materials. At different situations, some materials can switch from one type to another type, and we'll talk about that. Just because it's something is made out of a particular material doesn't mean it can't change types. But again, ferromagnetic materials have permanent magnetic moments, easily align with the magnetic field, high magnetic susceptibility, again, also can permanently magnetize. Paramagnetic materials, okay, do not have as high of magnetic susceptibility and also will not create permanent magnets. The most interesting type of materials are diamagnetic materials. In the presence of an external magnetic field, okay, their magnetization is actually in the opposite direction of the applied magnetic field, which means that they actually have a negative magnetic susceptibility. Okay, so let's look at what that means. We have this external magnetic field and we apply it to a ferromagnetic material. What will happen is the field lines will concentrate inside the ferromagnetic material and become more intense. The overall magnetic field is greater when we apply a magnetic field to a ferromagnetic material. Paramagnetic materials will concentrate this a little bit. Their magnetic susceptibility is a little bit greater than mu 0, okay? But again, not as great as it is for ferromagnetic material. Diamagnetic materials have a very low susceptibility. They will in fact repel magnetic fields or exclude magnetic fields. And a perfectly diamagnetic material will actually push out all the magnetic field lines, completely shielding the material. So where do we find these different materials? Well, the ferromagnetic materials tend to be iron, cobalt, and nickel. We don't show some of the rare earth elements, which are ferromagnetic in some cases, but in some situations we can actually alloy the ferromagnetic transition metals, iron, cobalt, and nickel, with some rare earth elements, creating an even better ferromagnetic alloy. Paramagnetic, most other materials are paramagnetic. Diamagnetic, tending to be more on the non-metal side over here. And again, here's the magnetic susceptibility of some different materials. Paramagnetic materials, again, you can see that chi here, the magnetic susceptibility is positive. And over here, for diamagnetic materials, it's actually negative. And again, somewhat surprising. You know, some of the Nobel metals are actually diamagnetic: copper, silver, gold, diamagnetic. Ferromagnetic materials, again, they can actually create a permanent magnetic field. And if we graph the magnetic field as a function of the applied field, what we notice here is we get this hysteresis curve, that the material magnetizes, and to demagnetize it we have to put a fairly strong opposing magnetic field on that. So if we magnetize, let me follow this properly. We start at 0, and we apply this magnetic field, it magnetizes, and it will stay magnetic even if we take the external magnetic field to 0. How do we get rid of the magnetic material? Erase the ferromagnetic material? We have to go to a negative field to get to 0, and if we apply a larger negative field, we get even more hysteresis on the other end. So ferromagnetic materials can be used to make strong magnets. They're also good for recording materials. Ferromagnetic materials don't necessarily stay ferromagnetic materials under all conditions. If I increase the magnetic field large enough, they actually transition to become paramagnetic materials. If we heat them up even more, they will transition to become paramagnetic, and this temperature at which they become paramagnetic is called the Curie temperature. This is very important because at 1,000 degrees Kelvin, iron goes from ferromagnetic to paramagnetic. Many of the rocks, especially the basalt at the bottom of the ocean, have large amounts of iron in them. So when they formed paramagnetic. They slowly cooled and retained the magnetic field from the Earth at the time that they were warmer than the Curie temperature. That field freezes into them as they become paramagnetic, and we can tell exactly where the magnetic field of the Earth was at the time that they formed. And again, at the Curie temperature, we transition to paramagnetic, but also as we put them in larger magnetic fields, they also transition to become paramagnetic too. Once again, a solenoid by itself can produce a fairly large magnetic field, but putting an iron core in the center of it, something with a high magnetic susceptibility, creates an even stronger magnet. And that's why many of these solenoids that are used as electromagnets will have a soft iron core to enhance their magnetic properties. Again, there is the equation for the magnetic field at the center of a solenoid. Here, if there's an air gap, mu is just equal to mu 0. However, with a ferromagnetic material, which has a high magnetic susceptibility, you can get an even more intense magnetic field. Again, paramagnetic, not as strong of a magnetic response. They do exhibit magnetization, which is proportional to the external magnetic field, but again, you can't really keep a permanent magnet there. Diamagnetism, these materials have almost no atomic magnetic moments. Most of the magnetization is induced by currents, which are, we'll find out from Faraday's law of induction later on. They're induced by currents from the application of the magnetic field. So by Lenz's law, something you'll learn about later on, they oppose the application of any magnetic field. The perfect diamagnet is, of course, a superconductor. Superconductors expel magnetic fields and will actually levitate magnets because of this repulsion of the magnetic fields lines themselves. So this magnet cannot sit on this superconductor because the magnetic field lines have been expelled, and this actually lifts the magnet up. It's called the Meissner effect, and it's simply the repulsive force caused by the material going superconducting and expelling all the magnetic field lines.